I am Jack Drinnen, for those of you who don't know. We've probably been chatting in some way on LinkedIn or Instagram, and that's how we've all ended up here. And today we're going to be talking about parametric design thinking. So I'm a parametric designer with quite a few years of experience. I'm a director at Tekne Lab, which is a parametric design consultancy. So working with architects, engineers, designers to support them with advanced pieces of design. And I also run Tekne Learn, which is a coaching program designed to help working professionals develop their skills parametric design thinking through Grasshopper. So I'm going to jump straight into all this because I realize I actually have quite a lot to get through in an hour. So I'm just going to jump straight in. So we're going to go through a bit of background on me, a little bit, just a bit of my background, because parametric design thinking really, ultimately is about how you approach logical thinking and how you approach problems. So it's quite helpful, I think, to get a bit of my background, where I started with Grasshopper, how this has developed over my career. So you get this kind of this background on me, this context for where we're going. We'll talk about parametric design thinking. What do we actually mean by this? How it might differ to how you're currently using Grasshopper. The benefits it gives us as designers, and we'll go through some of these core concepts of what I describe as core concepts of parametric design thinking. We should have time for some Q&A. You can ask any questions you like, and at the end, I'll just run through our Design Essentials program, which again is this coaching program aimed at working professionals. So, as a bit of background, I started using Grasshopper around 2010-11. So, for context, it's only 2007 was when the first iteration came out. So this was when I was at Masters, just obsessed with advanced pieces of geometry and natural patterns and systems. And this is why I started using Grasshopper in the first place. And we were really, really obsessed with these design to fabrication processes. So using using Grasshopper to create these really complex forms. We designed very complex surfaces in Grasshopper, and then we're able to fabricate them afterwards. So this is where my mind always was with Grasshopper. It was this tool of creation. It was always this physical output with it. I graduated, and I ran a abstract machines, which was a Masters of Architecture course at Leeds University, and I was also working for Nicholas Alexander, which is a fabrication company. And they started this 7-year period. I didn't really follow the normal route of an architect. I basically was just making for 7 years, and I have all these backlog of projects, which are full fabrication projects, working with different architects and designers, and every single one of these was Grasshopper was the core underlying process about how we developed all these projects. So working with tons of different materials, tons of different systems, different fabrication processes. And these are all live projects. And when you're using Grasshopper for live projects, you'll know that you have to make it work. There's no you can't fail. You can't fail at the last hurdle. It's everything has to be working. So we have a ton of these fabrication projects, which were again, there's lots of materials, lots of process, and really just pushing advanced pieces of design and advanced pieces of geometry to physical realization. Lots of installations and events, and again, Grasshopper, the backbone of all this. I was then picked up by Fossers and Partners because we were really interested in this idea of developing the architecture at this kind of one-to-one scale. So I was brought on to develop all these prototyping systems where we would feed into the design process. I was mainly on the Apple stores team, so we were designing these flagship Apple stores around the world. This real marriage of design and engineering with these stores. And all the while pushing my skills as a parametric designer, in all these interesting ways. And especially working with, there was the specialist modeling group, if anyone's familiar with these guys at Foster's, a really inspiring little group within the studio because they feed into all of the really great projects that Foster's do. So I was very inspired by what they did as a group and how they worked. And the two projects that really summed up my time there was because I moved out to Bangkok to work in the 𝗍𝗏𝗧 store and the Central World Apple store. The flagship stores here in Bangkok, and these really are, an amazing marriage of design and engineering. Every single piece on, this Central World project, for instance, was, everything was designed through Grasshopper and through to BIM, and all our drawings done in Revit. So this full design to fabrication process was really, achieved, in this project. And I kind of have to stop myself a little bit, and it probably could be the topic of an entire another webinar, because this project is, I can talk about it for hours, especially the stair is this beautiful piece of geometry that we designed. And all the while towards the end at Foster's, we were also working on these master plans, or actually these like generative master plans. So this is almost like how parametric design, I think, has evolved over the years, where it's not just about these super cool, really complex installations and set pieces. It's about how it infiltrates our daily workflow as well. And so all these facades that you can see are all generated. We're using heavily using BIM, but also driving complexity, change, and variation in all of our facades by using Dynamo and Grasshopper and these parametric workflows. So it's just quite interesting for me seeing how this has changed over the years. Extending these ideas of parametric design into a BIM environment, and it really affecting our day-to-day workflow. So from there, I set up my own company, again, inspired by, the SMG at Foster's. They were this parametric design group. So, how do you do this as a consultancy? How do you work with people to help them with their projects? And so these past few years, I've been working on lots of projects with different architects, engineers, designers, artists, whatever. And that's everything is driven through Rhino and Grasshopper and through to BIM as well. So these are fully generated facades using Grasshopper and Rhino inside Revit. Really complex setting out of facade elements, and it just supporting different studios with all this type of work. It's actually really hard to develop in-house for small studios. So again, full fabrication systems for these facades, but also working at more conceptual levels with early concept designs for these malls. And more recently, there's a tower. Those are just work in progress, but a tower I'm doing in Bangkok, and an extension to the airport here as well. And again, all these parametric facades that we're working on. I'm doing a lot of facades at the moment. The setting out of this, and again, everything feeding into this BIM environment. Tekne Learn is just aside from this. So I've been using Grasshopper so long. I get asked a lot to train people. So working with the students at my unit back in the UK, at the Abstract Machines unit. So we were constantly running sessions with these guys. I've ran sessions for different studios, different individuals, you name it. Over the years, I've done a lot. And last year I was out in Rwanda with a mass design group. Not sure if any of these guys are on the call, hopefully. But I get basically a 3-week long course with them, intro to expert level with their engineers and architects. And this has really turned into a coaching program, so an online platform for architects and engineers and whoever's looking to learn parametric design in a more systematic way. So that's kind of my 10 years or over 10 years worth of parametric design in 5 minutes. So I wanted now to jump into what this idea of parametric design thinking is, using Grasshopper. And it's quite interesting to think of actually what it isn't in a little way, and these common use cases of what Grasshopper, of how people use Grasshopper. So this idea is writing a script and using it once is not really parametric design thinking in my mind. Downloading other people's Grasshopper scripts is not parametric design thinking. Only running, a lot of people just use Grasshopper for like environmental analysis, and just probably maybe scripts people have downloaded. Again, this is not really delving into the what parametric design is for our workflows. Only following YouTube tutorials, this isn't really going to teach you parametric design. It'll teach you how to do something. It won't teach you really, a lot of the time, it won't teach you why you're doing anything. I hear people say Grasshopper requires a thinking that's not really natural for me, and that's because it, generally it isn't. It's a skill that we acquire. I can use Grasshopper, but I can't build my own script from scratch. This is super common. I just flatten randomly and graph randomly until it works. And what is a tree? What is a data? What I see a lot is this lack of foundational knowledge in Grasshopper. So, and the reason for this is most people, when they start out, is that they approach this from a modeling mindset. You may have come from Rhino or SketchUp or any other 3D modeling program, and the way you approach Grasshopper you can't approach it like this, because you quickly start using really complex geometry very quickly, and this slows down your whole process, slows down your learning, really bogs down what Grasshopper does best. And parametric design is really fundamentally about designing systems rather than objects. This is such a key, and we'll talk about this a little bit further because a little bit later on, because it's so key. But the key word here is like the ability, the ability to break down an object system into a set of parts and elements that you can plug back together. And again, this is an ability. It's not something you can just do. It's something you have to work on and train to do. It's like learning a language. You have to be using it every day, using it often to get a lot from it. Students tend to miss out these core concepts, what I call core concepts of parametric design, and then it's kind of hard to get over this. So just like learning a language, spending the time to learn these core concepts of parametric design will lay these foundations for you moving forward. So these core concepts, what are we even talking about? So I have these in 4 broad categories that we're going to go through sequentially. So number systems, data structures, building complexity, and storyboarding. So we'll start with building complexity. And there's this understanding that the basic building blocks of what we're using as a parametric designer are numbers. They're right over here on the left. Numbers are the basis of creating points. 3 points make a coordinate system. From there we can create vectors and planes. We use these to define our curves and our line work. We use these to define surfaces. And then we use our surfaces to define solids. And there is this feedback between the first 4. So sometimes, there's this arrow of complexity that we're building up throughout these objects. But there's this also feedback mechanism, because we may break down our surfaces at some point to find information about them and feed these back into our workflows. And if we keep this within numbers, points, curves, surfaces, Grasshopper is super happy. Rhino is really quick. The computer can work very efficiently with these objects. As soon as we go to solids and big, heavy operations like Boolean operations, this is where everything bogs down and slows down. So this arrow of complexity is super important to keep in mind. And this is the first one I want to show you, because I'm going to go through a live demo, and we're going to see how this works in practice. So we're going to tackle now number systems and data structures. We're going to do this in Grasshopper, and we're going to do this as a little example. And we're going to build this this roof, which is the Changi airport roof in Singapore. So it's a beautiful diagrid roof that ends in this waterfall in the middle. I don't know if anyone's been there, but it's worth a visit. So we're gonna build this over the next 20 minutes, 30 minutes, and learn some things along the way. So I need to hide this, and I have my Grasshopper ready to go here. So the first thing that we're going to do is we're going to start defining some curvature. And I mentioned that numbers create points, create curves, and sometimes, with this flow of data, sometimes it's actually easier to start with what you're aiming to do. So I'm actually going to put my curve on first. I'm going to use this 𝗟𝗓𝗡 curve and look at the inputs it's giving me. So the main input really is the first, what are the points defining this curve? So we can answer this question immediately with an XYZ point. That can go into here. Now we get an error because you can't draw, the XYZ point is already outputting a point because it already has some inputs in here. But you can't draw a curve with just one point. This is why we're getting this red error. So we need to input some information into these X, Y, and Z coordinates. So we're going to use this to understand some number systems and create some number systems. So the first number system that we're going to use is a series. And I'll just quickly draw and explain exactly what we're aiming to do here. So we're going to draw a list of 4 points along our X axis. So this first point will be at 0. The second point will be at, say, 50. I can't draw very well. Then 100 and 150. So we're using this series of numbers. It's basically the 50 times table up to the 4th value to create this X, this X value of our point. And then we're going to create another series of numbers to create the Z value. So this is what we're going to do. Let me clear my drawings. Okay, so let's tackle the first X values first. So we can look at the input of our series. Got a panel because you can see it's already working, and we have this list of 10 numbers already. And this is because there's already some values in here. So I'm just going to change these. We said we're going to have a division of 50 in the X direction. So I'm going to put a number 50 in here. I'm going to copy and paste this, and I'm going to, I'm already getting my 50 times table up to the 10th value, but I'm just going to cap this at 4. So you see, all this is just a list of numbers, and this is going to define our X value. Our curve is happy now because we actually have more than 1 point, which is great. And so now we're going to define the Z height of these and create this really beautiful parametric curve. So I'm going to just do this a different way with a slider. Actually, I'm going to just type 100 because it's a quick way of making a slider that's capped between 0 and 100. I'm going to copy and paste this 4 times. And I'm going to merge these together into one list. I use merge a lot because we see the order that things are entering and these numbers are in. So these are going to become our Z values. And now we have this really nice control over our curve. So we're just going to think about that profile of the Changi Airport roof. Let's say, okay, maybe something like this. And so we're now building this beautiful curve. So we're going to understand a little bit more. We're going to just delve into a bit of curve properties, just so we can understand how to use this properly and how to develop a nice parametric script. I'm going to unhide everything apart from the stuff I'm working on, just to make this a bit easier. So the first thing that we're going to look at is, what we're going to define some points on this curve. So I'm going to I'm going to use the tool evaluate curve. So I'm going to evaluate a point on this curve. And just to understand the world of this, or the properties of this curve, I'm just going to measure its length. So if I measure its length, I can see this is reporting that it's 179, say, meters long. We're working in meters. And this is obviously, associated with this curve. If I change these points, this number updates because the curve length is changing. So say if I wanted to find the halfway point of this curve, I would, let's say, I'm going to add a number slider in here, and halfway along that curve is roughly 100. Yeah? A quarter of the way along is roughly about 50. If my curve length changes drastically, so I now have a much longer curve, this is not parametrically updated. My understanding of my curve is kind of incorrect because I now have to change this number to be able to find the center of the curve again. And one of the ways around this is a really, really, really important concept, and write this down for parametric design. This is this idea of reparameterization or normalizing. So what I'm going to do is I'm going to right click on my curve here. I'm going to reparameterize it. So what reparameterizing does, it sets my curve length now is not being understood between 0 and 280. Because, my curve could be any length. I could be working on a teacup, which is, millimeters, or, a skyscraper, which is hundreds of meters. I've reset the domain at the start and end of my curve between 0 and 1. So if I put a slider in now, that's just between 0 and 1, I get full range of this curve. I can see every point on this curve, and it's just because I've reparameterized it. Halfway through the curve is 0.5 and so on. So what if I wanted multiple points on that curve, I now can just, as long as this number is between 0 and 1, I can add as many, parameters as I like to choose some points on this curve. So I'm going to now introduce, I'm just going to delete my sliders, but I'm just going to introduce now another number creation tool. So we looked at the series, which was that the tool to make basically the times tables, essentially a sequential list of numbers. So now I'm just going to show you the opposite, well, not opposite, but a different one called range. So a range creates a division of numbers on a domain. So what that means is I have my input of my domain is already set to 0 and 1. A lot of components in Grasshopper are already set to 0 and 1 anyway, because of this reason, because curves and surfaces are really happy operating in between 0 and 1. So this is already set between 0 and 1, which is great for me. And I have 10 divisions set in between 0 and 1. If I set my panel, if the input to be, say, 2 divisions, I'm going to be able to, I'm going to create a list of numbers that's 0, 0.5, and 1. And if I use these as my curve parameters, because my curve has been understood between 0 and 1, I can now address and increase these, how many divisions I have along my curve. And this doesn't sound like massively interesting. You might be like, well, why are you doing it like this? We have lots of curve division, tools up here. And this is a really key bit of, I'd say, knowledge of parametric design thinking, because when I'm just going to preview this up, and when we use this curve divide, we get no control. This is a uniform set of divisions over this curve. So we don't really get any control, or I can actually unparameterize this. This is doing a lot for me. It's already reparameterizing it. It's already, the n value is basically how many. So it's doing a lot of work for me already and reducing my control as a parametric designer just by using this divide component. By doing things like this, where I am evaluating the curve like this, and I'm understanding that, it's doing the exact same thing as the divide, but I'm doing it in a way that I can control. And one of the reasons is we can do more advanced things like use graph mappers to take my list of numbers. A graph mapper is essentially going to, oops, sorry, I want to use this conic. So what's going to happen is my list of numbers is going to get plotted along the bottom of my graph mapper. I'll put this down to just 2 numbers, just so this is really clear, because this is really, really key. And what's going to happen is my number at the bottom, all my numbers along the bottom, my 0, 0.5, and 1, are going to get mapped, projected onto this curve, and mapped over to this next axis, the x-axis on the right hand, on the left hand side. So you can see my 0.5 is being adjusted constantly. What this does is when I increase this to, say, 50 divisions, I get this awesome control over my points. Oops, sorry, I need to actually use these. I get this really, really fine control over my points. Essentially, we have number systems that are uniform and number systems that are non-uniform. And this non-uniform way of making numbers using just by using this graph mapper, leads to some really, really cool things that we can do, with complexity-wise. So understanding this is key. By just using this divide, you miss out all this knowledge that you gain from using these sets of components. So I'm just going to park this up here, preview off. And what we're going to do now is going to increase complexity again, and I'm going to create a surface. So I'm going to take my curve, this curve, actually, I'll copy and paste this one. I'm going to take my curve. I'm just going to adjust it back to the Changi kind of airport model, because we're still aiming for Changi Airport. I'm just aiming to talking around the subject a little bit, so we understand a bit about these components. And we're going to revolve a surface. So surface revolution. We're going to basically sweep this curve around the central axis to create our dome. So I'm just going to create an axis with a line SDL and a Z, not Z, and XYZ point. So this one, and we now have this D input, which is basically what domain, how much you want to rotate around the center. And it already has this D input as basically 360 degrees, and which is a domain. So I'm going to construct a domain, and I'm going to reset this because I want to control this just so we can so I can explain a few things as well. So I'm going to add a panel with 360, and the domain, when Grasshopper uses angles, it uses things called radians. So we need to convert our degrees to radians so we can use this as an input. And oh, actually, sorry, I should use a slider as well. Slider, and I'm just going to set this to the maximum value of 360. And you'll see how this works. Our sweep is now just going to be rotated around this curve, around this center point. And the other thing I'm going to do is I'm going to add, because we have this oculus in the middle from the Changi airport. So I'm just going to add a bit of space in between, so we create this central oculus. So basically, rather than my X value starting on 0, it now starts at 50. And I can control the dimension of that central oculus, or the central hole in the middle, because my curve has been offset. So we now have a surface. And I'm going to explain a few things about surfaces, because the way that Grasshopper interprets surfaces and curves is incredibly similar. So we're going to do exactly what we did before with our surface. With our curve up here, but we're going to do it with our surface. And I'm going to reparameterize my surface straight away, because surfaces can also be understood and evaluated between 0 and 1. I'm going to, instead of evaluating curve, I'm going to evaluate surface. And instead of putting one number in, which is, which was the number to select where we wanted on our curve, we now basically need a coordinate. It's asking for a UV input. So I'm going to use another tool called a multi-direction slider, which already has its domain set between 0 and 1. And now, if you see, if I set my analysis point, or my UV point, to 0, 0, I can see I have two axes to my surface. I have my V axis along this side, and I have my U axis along this side. And just by inputting two numbers, and these are just numbers, I can select anywhere on this curve, on this surface. We can also, so we're going to do the same. We're selecting a point here, but we're also going to divide the surface. So in the same way that we divided a curve, I'm just going to preview as I go. We have the ability to divide this surface up into smaller surfaces. And the tool that we're going to use is this. I go to surfaces, is this ISO trim. So the surface that we're going to break up is this, and we're going to use this tool called basically divide domain squared. Is almost like your range function. It's taking your domain of your surface, which is 0 to 1 in both directions, and it's going to break that up into a UMV, into UMV coordinates or UMV domains. So I'm going to add some sliders into here. So we'll have 10 in the U and 10 in the V, and you see how this works when I put this in. We'll be able to divide my surface up into smaller surfaces. So I'm splitting this up using a domain. And if I look at here, and I'm just going to set this to 1 by 1, because you can see the UMV domain in both directions is 0 to 1, 0 to 1. So I'm basically, I have the whole surface. If I divide it by 2 in both directions, I create 4 surfaces, and then so on, 8 surfaces, 9 surfaces, so on. So we can create geometry, and then we start dividing it up afterwards to do something with it. And that's what we're going to do now. I'm going to show you how to create this diagrid surface. So I'm going to take these surfaces, and we're going to just draw a bit of geometry on it. And notice I'm not breaking this up. I'm not dividing my surface just yet, because I just want to show you how this works. So up to now, we've just been talking about numbers. These are number systems with our range, number systems that we've input, we're making curves, we've created a surface. We're just operating on one, in one list, one branch of the data tree. So we're going to design this next part, so it's going to work on multiple levels. So what I'm going to do is I'm going to turn my complex surface into 2 flat panels. And I do this by deconstructing my breadth, and I can find my vertices. So again, this is that loop of data. We're not going to solids at any point. We've got to surfaces, and now we're breaking these surfaces down into some elements that we can use. So this, I'm going to grab the vertices of my breadth. I'm just going to put on this points list because it's really helpful. Really helpful for you to be able to see the list of points. Oops, a bit big. So what I'm going to do is I'm going to draw a surface from my and these are just the corner points. So these are just now points, and I'm going to draw a 3-point surface from my 0 point, my 1 point, and my 2 point. So if I go to surfaces again, I have this 4-point surface tool that I'll use. 4-point surface still works with 3 points. And I'm just going to copy and paste this, and we'll make another surface between the other 3 points. So this looks really weird because this surface is really exaggerated. But if I hide my this one, I don't know, there's a surface that's on somewhere here. So I basically turned my surface into 2 triangles. But what happens when I increase the density of my divide? I have to turn these points off. We now essentially created our 3-dimensional surface from flat panels. And what we're utilizing here is this branch structure of Grasshopper. So when we just had one item, we were creating lists of surfaces in between these lists of corner points. But when we use this deconstruct breadth, what it does is automatically adds branches and structure to our data. So we don't have to do this over and over. It'll carry on working individually on each branch of our data tree. And these are really important concepts to learn. So I'm just going to set this back down to 1 again, just so I can see this kind of working. I'm going to create the diagram structure as well. So let's say I'm going to create a line here from my corner points and the other way, and I'm going to pipe these lines as well, just to create some geometry. So this is all I'm creating for every single surface. So when we increase our divide, we have the ability to create this diagrid surface, and because we're still actually we haven't rotated fully through our 360, we can complete our surface by increasing our revolution here. It's just easier to explain how these surface properties work when we're not using a fully rotated surface. And so we can, we can change the amount of divides in the U and V. So maybe we should up this to, I don't know, to something like 50 here. And we could do not 50 in that direction, that would be too many, 10, something like that. So, already we're getting this quite beautiful diagram structure being created. But there's a few things that I'm going to introduce because we can do more complex things than this. And this is where this idea of using numbers to drive geometry works. So it's a bit unsatisfying that every single bit of structure is the same. So what I'm going to do is I'm going to give them all a different radius to my for every single bit of structure. So what I'm going to do is I'm going to find the center point of all my surfaces. I'm going to find I'm going to deconstruct those points. So I'm basically finding the center point, so dissolving, finding some information from the surface again, finding the Z height, which is this one here. And I'm going to use this to create my radiuses of my pipes. And because all the branching structures, all aligned, I could just use this directly. My problem is that these numbers are way too big. We were drawing a pipe radius of 1, and now I'm creating pipe radiuses of like 50, because this is a dimension, between the Z height dimension of the point, and we use it as radius. So this isn't going to work. And the process that we do to take numbers from one system to the other is called remap. We're going to take these numbers, these Z height numbers. We're going to find out where they are. We're going to find their upper and lower boundary as a list of numbers. So I can see if I look into this this list, I can see that the lowest panels are 2.5 meters high. The highest panels are 50. So this is the boundary. This is the range that they operate in, and we're going to remap these numbers to a new domain. That we can define. We can define the upper and lower boundary of this domain. So I'm going to make the lower boundary say 0.2, and I'm going to make the upper boundary say 2. And these are the numbers we're going to change. And now by controlling these numbers, we get this beautiful, I guess, a blend of structure and members. The higher they are, in this circumstance, the fatter they are, the wider they are, the radius, the lower they are, the thinner they are. So, we could do this in the Y vector. So, from one side to the other, we could do this in the X direction. That'd be fine. We could also find so if we find our center point again, and we do a distance, we could put an attractor on this. So the distance between our center point and our origin point could also be this. So the further away they are from our center point, the wider the radius. And again, we always have control over the number here. So, all of these lessons is it's driving geometry with number systems. This little knot of remap is and changing numbers from one system to another is so integral to parametric design thinking, how we do things in Grasshopper. And so some of you may have picked up on a kind of something I deliberately left out, which was that when we were looking at our curve before, and we used this remap to I actually said when we divided this curve up, it's you're not getting a lot of control, you're just dividing it in a really non-uniform way. It's only by using this range and this graph mapper that we can get this real complex setting out and non-uniform numbers. So you may have noticed that I didn't actually do this when I subdivided this. I am just dividing my my surface in a really boring way. It's really uniform in the X and the Y. So, the question is, can we do, can we make a really complex setting out of our surfaces so they're not uniformly set out? And the answer is yes. So we're going to take this range in this graph mapper. I'm just going to copy and paste it down here, and we're going to create 2 lists of numbers now, using and creating a real complex domain setting out.
Sur le téléphone, sur le casque, ça marchera pas.
So we will come to mathematics. We're going to so if everyone could mute, that'd be great. Thank you. And we're going to use a few tools. Honestly, I'm not going to go through it completely just because of the time of this webinar. But we can use basically these domain tools to create this complex setting out. So again, this is just lists of numbers, you know. I'm going to put 40. I'm going to match the same numbers that I have in here. These are just lists of numbers that I'm creating this complex domain with. And once I do this, there's a bit of understanding of how lists map each other here. So I'm going to have to graph this. I get this real fine control over my surface. You know, I can bunch them up towards the edge. Actually, my height is a little big, so I'm going to make this a 1. Actually, no, 1.5. So yeah, I can create this beautiful blend of all my surfaces. I can make them closer together towards the edge, and they spread out towards the middle. And this is the kind of this is the kind of parametric control over your geometry that you need to do these complex pieces of design. And all this is number systems and understanding data, really, you know, and this idea of this complexity workflow. So I'm going to go back to my my PowerPoint. So we got kind of close, and I'm just a little bit wary of time, so I'm just going to speed through this. So we got kind of close to this. You know, when I see things like this now, I just see, you know, surfaces and surface parameters. You know, it takes time to develop these skills, but you just start seeing grids all around you. The next, so we've done number systems, data structures, building complexity, how things feed into each other, and extrapolate data. But once we've understood all that stuff, we're still faced with this challenge as parametric designers, because, you know, how do we take a blank canvas and how do we start scripting? You know, you have an idea of what you want to do in your head, but where do you start? It's really challenging. And so I'd like to develop this idea of storyboarding. We do this anyway as architects. You know, we love to make diagrams and you know, this real logical sequential steps of ideas to describe our architecture. And so this idea is really relevant for designing things in Grasshopper as well. And I have these templates which I'm very happy to share with you. That I'm just going to do a quick demo of you know, how do you start a project? How do you start something from scratch? So this is ridiculously, it's probably the most complex parametric table that's ever been needed. But you know, we'll go through this table. It's not really there to tell you how to do it. It's just to get you thinking about how you might go about breaking up this geometry into a parametric model. So we go through all these questions like, you know, what do we need? We need polylines. It's going to be a single object. We're going to build it in place. That's my strategy. The primary orientation is uniform. It's not non-uniform. Everything's pretty uniform around it. And we start answering these questions. We write out, like literally write out on these templates, you know, what are the parameters that we want to change? The height, width, length, the depth of the top, the legs, you know, the offset in, and we start drawing these like comic book strips essentially. You know, so number 1 is define the top curves, height, width, length, rectangle is needed, you know, writing down components that we might need. The leg location, we offset from that, and it's this real logical step of sketches. And we use these to write our Grasshopper scripts. You might see the blue components here. These are from a plugin called Telepathy. If you start using Telepathy now, it will neaten up your scripts and your workflow is so much easier. So I would suggest starting to use it. You know, and all these little sketches, you know, they become our Grasshopper script. You know, so here we're just defining a plane for our rectangle, defining the domain of our width and our length. The same for, you know, this is offset, finding those center points. You know, using a rectangle to create our leg profiles, and then finally extruding geometry. Again, it's the most complex table ever that you don't need. you probably wouldn't need to do this, but it's to highlight this arrow of complexity. You do your heavy operations at the end, and everything sequentially follows on like this. And then the idea is that, we're designing systems, not objects. So, from your one table script, you can now design, hundreds of tables. I love this analogy of a bike. And a bike is just a collection of components and things that go together. So there's a frame and wheels and spokes and pedals and whatever. They all fit together in a way that defines the function of a bike. And this is the underlying system. The design comes in when we're designing, race bikes or BMXs or kids bikes or whatever it is. There's a difference between the logical underpinning of what creates the object and the design of it itself. And this is what you, as a parametric design engineer, used to. You're designing systems, not objects. So starting with this reference image idea, going through these checklists, creating your global parameters, storyboarding this out, feeding this back into your parameters. You'll basically learn as you're going along through this process. Sketch scripting this stuff out, testing it, and how it all feeds back into each other. So another super quick example, just this parametric roof. Again, go through all these checklists. How I might do it. Again, it's not the answer. It's just to get you thinking. Okay, well, I can see a module. Maybe I could take these two edge curves to create this module. I'm going to define all that from a base triangle or a base polygon here, sorry, and a center point. So I can start sketching this out, mapping out how this might work, and this feeds directly into what you do in Grasshopper, really sequential. And because I'm using this linear process, I can update my polygon. I have number of sides as a input, so I can create not just one, but like 10, 20, as many iterations as you want of these things. And I really like to use real-time rendering to visualize my scripts as well, because connecting visual imagery with your script is super important as you're developing yourself. These are all done in D5. My parents using D5 yet, but I love it. So these are the core concepts that I would describe as parametric design thinking. And when you get used to using these, it's this holistic approach to all these concepts, and it's this fluid connection between them all. So you'll be storyboarding in your head while you're thinking about number systems, and parametric design thinking is this on a holistic level, and the ability to apply this kind of design thinking to any kind of problem is the goal. You start to see the similarity between really different pieces of design, because on a systematic level they are like nearly identical or very familiar. And the best analogy I like for this is it's like learning all this for yourself is like how you learn to cook. You can watch YouTube videos, you can get cookbooks and whatever. You can learn to cook in your house, it's fine. But it doesn't make you a chef. When you come to sit down and write your own recipes, you need like core understanding of what goes well with each other. How do you build a recipe? And that's the similar to what we're talking about here. And when you get good enough at all this stuff, you can pick your recipes off your shelf. You have this back catalog of imagery, of scripts that you can pick apart and you can use when the next time you come to start something new, to start a new recipe. So this is, I guess, my kind of summary of parametric design thinking. So we can open up now to a Q&A. I've been talking now for about 50 minutes, so maybe does anyone have any questions? Would you like to maybe you can ask in the chat if you prefer, if you're more comfortable. Yeah, anything here that you would that you'd like to discuss or talk about?
Hello, sir. I would like to have to ask a question if it's possible.
Hi, yeah, of course.
Hi. Yeah, actually, I'm a beginner in parametric design, and I am trying to work with Dynamo. Actually, not Grasshopper, but I think they are, in principle, it's similar to each other.
Yes.
For a beginner, actually, when do you think that you have to stop in a process? When you start, like, analyze a shape and you want to do it, and you start your way with knots and everything, but you don't get the result that you are waiting for.
Right.
So when you have to stop and start again. And
stop and start again. It's interesting.
And the other question, actually, for a beginner, if you want to start, should you, or have you, or do you have to know every small detail about the node that you are using, like the why and how and information?
Okay, well, these are great questions. So I'll tackle your second question first, because again, this idea of parametric design thinking in my head is it's about how you approach things. So you don't need to know every single node or by any means. You just need to know enough, you know, that your own kind of workflow about how to approach these things. You will approach things very, very differently to how I would approach problems.
Mm-hmm.
And it's super interesting working. Some people work very numerically, some people work very geometrically. And we all constantly are coming up with different you know, ways of doing exactly the same thing. And neither of them are right or wrong. It's just they're conceptually different approaches. So yeah, by no means you need to know every single node. You just need to know the you know, the ones that you use, the ones that you associate more with your process. And again, the analogy of the chef, you know, it's you know, how do you approach your flavors, let's say, and what kind of things that you like to use within your cooking. This is how you extend the analogy. In terms of your first question, you know, when you stop, I guess when it's not working, this idea of storyboarding here, I think, is a good idea, because you could. If you're really trying to break down your script into you know, small enough chunks, small enough components, then actually the end goal gets built very sequentially. So 50% of your script might work perfectly, but it just might be the end 50% that you need to work on. So there's no real, like, you might design, you know, 5 maybe or 2 or 3 ways of doing the second 50%. The first 50% is completely fine, it works, you're happy with it. But it's just, you may work on multiple versions of the second half. So I wouldn't say there's any point in, you know, I guess actually the advice would be try every idea out as far as possible. And only when you're really, really stuck, go back a few steps and maybe try and come up with a different idea or a different approach and try that one. You do this a few times, it will be a combination of one of the 2 or 3 ideas. So it won't be rewriting the whole script. You'll just need to write parts of it, because you've already broken it up into these really you know, these really isolated sections or steps. Does that answer your question?
Yeah, absolutely, kind of, yeah, because I think that as you mentioned, everyone has his own way to do it. And but what I'm sometimes struggling with is that to understand this node, what it's the input that it needs and the output that it gives at the end. So maybe with practice and more practice, the one will achieve it.
It's totally just, it is practice. It is over and over again. You know, like learning a language, going to the gym, you have to keep using it, use it daily, you know, to create your own thing. And any other questions? We are running up to the hour time, so maybe time for one more question. Okay, then I'll leave it there. You can, you know, send me DMs in LinkedIn. That's totally fine. So look, Thank you very much. Thank you for the questions. That was really great, and happy to have that feedback. So, the concepts I've touched on today, they're just, a brief overview of this idea of parametric design thinking. And I understand there's a ton of information to kind of absorb in 1 hour, but this is all these concepts are a underlying part of the Grasshopper Design Essentials program that I run. So I just want to share a little bit more of information here with you. So what is it? It's a 9-week program what is it? It's a 9-week program looking at building foundational knowledge of Grasshopper from the ground up. And we use all these systematic methods that we have been talking about in this webinar. So we build up your knowledge and experience of complexity through live projects and design exercises. Who's it for? It's for students, professional architects, designers, engineers, anyone looking to develop their Grasshopper skills in a systematic way. How does each of the 9 weeks work? Well, you get video content that you have to work through. So there's a few hours of videos, introducing these core concepts and ideas. You have design challenges that are associated to these videos and apply what you have learned in those videos in a really practical way. And these are in 3 or 4 levels. So there's always, scope to challenge yourself and push yourself. And this all feeds into a portfolio that we build over the 9 weeks. Again, connecting imagery with our scripts is super important, and for you to develop your own approach of parametric design thinking. Each week you'll have a one-on-one call with me to discuss anything in depth. There'll be group calls where we talk about everything with the current cohort, sharing experiences, sharing different ways of working, and sharing our images and everything. And then you'll also have access to a Discord community, which is our platform where you can, you're never very far away from an answer. Just throw your concern or query or question up in the Discord community, and I'll answer in a few hours when I've woken up, or someone in the community will answer. This is just a few of the images from our current cohort of students. So again, imagery is super important. Building your own approach and your own library of parametric scripts that you can take into your work. It's around 6+ hours a week, so 2-3 hours of videos, 2 hours plus of design challenges. Depends how, you could take a lot longer if you really, really want to push yourself. The one-on-one calls are about an hour, half an hour to an hour, and then the group calls about an hour. And keep in mind, this is super flexible. So the videos are like 20 to 30 minutes, with some 40 minutes, that you can fit around your schedule. And then after the 9 weeks, we also have the Tekne alumni Discord channel. So you'll go into another private channel. And, this is to provide support ongoing. I don't just want to, leave you out cold on your own. Develop this as a community. So you'll have a place to ask questions, post, and, take part in the weekly or fortnightly design challenges that get posted up there.